Next, we're going to do shear and moment diagrams on frames. We have vertical and horizontal members. Does that cause a problem? No, but we need to be aware that shear forces are going to become normal forces and vice versa. So if I take this corner right here and I expand it out to the vertical member, the corner, and the horizontal member, I'm going to have internal forces of shear, normal, and moment. On the horizontal piece, I am also going to have shear, normal, and moment. And I sum for forces in the x direction. I will have minus shear 1 plus normal 2. So shear 1 is going to equal to normal 2 because they both happen to be acting in that horizontal direction. Let's say, for example, I have this frame that is pinned at A, C, and D. We have 2-point loads between B and C, and we have a distributed load from C to D. I want to find the shear, moment, and normal diagrams for this frame. I'm going to start by solving for the reactions. And I find that AX is equal to 45 kilonewtons to the right. AY is 83 kilonewtons up. DX is 45 kilonewtons to the right. And DY is 7 kilonewtons up. I solved that with statics, breaking this apart. Next, I'm going to create my diagram lines. So I've got shear, positive, negative, moment, positive, negative, and my axial tension and compression, or positive, negative, both work. So shear is everything that's going to be acting perpendicular to my member. So my member is vertical, so shear is going to be horizontal. So I've got 45 kilonewtons moving to the right, and then I have nothing changing that all the way up the member. My moment diagram starts at 0. I do not have a moment at the pin, and it's going to change the area under the shear diagram. 45 times 4 is 180, and it's on the negative side, so my moment is going to move negative 180. And I have a constant shear, so I will have a constant slope to my moment diagram. Last is my axial force diagram, and I've got my 83 kilonewtons acting up, which is compressing my diagram. So my axial force will be 83 in compression for the entire span of the member. So now I have corner B. Corner B, if I've got shear acting to the right at A, it's going to be acting to the left on B at the member AB. So it'll be acting right on corner B. So this is 45 kilonewtons. I already said that 83 was in compression, so it's still going to be compressing that corner. And we have the 180 causing compression on the right side, 180 kilonewton meters. And that is 83 kilonewtons. I do not have any forces acting on corner B. So summing forces in the y direction, my shear on the horizontal portion of B is going to be 83 kilonewtons. My normal is going to be 45. And it's going to be in compression, so I'm going to switch that arrow. And then my moment is going to be clockwise 180 kilonewton meters. Now we can move to this horizontal member. We have an initial shear of 83 kilonewtons down on corner B, so that means it's going to be acting up on the horizontal portion of corner B. We have no changes until we get to that 50 kilonewtons, so we're going to drop down to 33, no changes. Drop down to 7, come across, which means we'll need to come back up 7 for this horizontal member to be in balance. Moving to my moment diagram, I start with compression in the bottom of 180 kilonewton meters. And then I'm going to increase the area under the curve. So I've got 83 times 1.5. So this is going to come up here to 55.5 constant. And then I'm going to come up again, 33 times 2, so that's 66. That's going to get me up here to 10.5. And then I have 7 times 1.5, which is 10.5, so we get back down to 0, which is good. We're at corner C, which is a pen. Pens cannot carry moment, so I need that one to be 0. Unlike corner B, which was a fixed corner and could carry moment. Next, I have my axial force diagram. I have 45 in compression, so that means all the way across here is 45 in compression. Now I can come look at corner C. So corner C is 45 in compression. Horizontally, coming for that horizontal member, shear is -7. I do not have moment because it's a hinge. So that means I'm going to have shear of 45 kilonewtons for the vertical portion of C and a compression of 7 kilonewtons for my vertical portion of C. Last, I have my vertical member on the right from C to D. So starting with shear, working from top to bottom, because we've been going clockwise around our frame here. I've got 45 kilonewtons to the left acting at C, which means it's going to be acting to the right on member CD, 45, and that is going to change 15 times 6, which is 90, over the entire length. I now have a point of inflection for my moment diagram. So moment diagram starts at 0 because I've got a pen at C. It's going to change 45 times 3. This is symmetric. So it crosses the middle here at 3 meters, which means it's 3 meters at the bottom. So my maximum moment is going to come up here to 67.5. And we've got a first degree constantly changing, which means my slope is going to constantly change. And then we're going to come back down here to 0 because we've got another pen that cannot carry a moment. Last, I have my axial force diagram that is 7 kilonewtons in compression. And here we have our entire shear and moment diagram system. The important thing here is to carry everything through the corners so that shears and normals get worked out between vertical and horizontal members. Now let's look at this frame. We've got a roller at A fixed corner at B, and a pen at C, and I want to find the shear and moment diagrams for this frame. I'm going to start with solving for the reaction AY. So I can use that to make my shear diagram. Summing moments about C, counterclockwise is added. 0 is equal to minus AY times 21 plus 220, the applied moment. And then I have my distributed load. So that's going to have a resultant force in the middle here of 80 times 15, which is 1200. And it is acting at half of the height and half of the width. So the horizontal component is 960. So this will be acting perpendicular, right? So if this is a 345, then this is a 435. And my vertical component is 720. So we're going to add 960 times 6 and 720 times 4.5. And we end up with AY is equal to 439.048 pounds. And that ended up positive, so it is acting up. I am not going to solve for the reactions at pin C using X and Y directions because I need them to act parallel and perpendicular to member BC. So we're going to wait and solve for those later. Starting with member AB, I have a vertical reaction at A. So drawing on my shear diagram, I go up 439 pounds. Moving to the moment diagram, I need to first change the positive area under the shear diagram. So that's going to go up from 0, 439 times 6 feet to 2,634. Then I have the applied counterclockwise moment at A to B. It's a positive moment, so internally it's going to drop 220 down to 2,414 pound-feet. Then I add my last area under the shear diagram, which is 439 times 6, and I end up at 5,048 pound-feet for my moment diagram at corner B. Last is my axial diagram, and I do not have any axial forces due to that roller at A, so the axial diagram is going to be 0. In order to move on to member BC, I need to look at corner B, which has a shear of 439.048. My axial force is going to be 0, and my applied moment is 5,048.57 with compression in the top. I'm going to have shear running parallel to the surface and normal running perpendicular. There are no distances at a corner, so my moment is just going to be equal and opposite at 5,048.57. Summing from my forces in the X direction, I'm going to have 0 is equal to minus 4/5 of my shear V plus 3/5 of my normal force N. Summing for my forces in the Y direction, I'll have 0 is equal to 439.048 minus 3/5 of shear minus 4/5 of normal. Solving simultaneous equations, shear is 263.4 pounds and normal is 351.2 pounds. I can now solve for my free body diagram BC. CX is going to be the 351.2 pounds because there's nothing else in the X direction. Summing forces in the Y direction, we have 0 is 263.4 pounds minus the 80 times 15 load plus CY prime, and we will get CY prime to equal 936.6 pounds. We can now draw our shear diagram. So starting at a positive jump at B, 263.4. Then we're going to subtract the area under that evenly distributed load of 1,200, and that's going to get us down here to 936.6 pounds. Solving for x, I have 263.4 divided by x set equal to that 1200 divided by 15, and we find that x is equal to 3.2925 feet from B. I can now start my moment diagram, which starts with a positive 5,048, and then I'm going to change the area under my shear diagram, so that is 1/2 of 263.4 times 3.2925, and that's going to get me all the way up here to 5,482. I have a constantly decreasing positive shear, so I'm going to have a constantly decreasing positive moment slope of 2 degrees. And then I'm going to subtract the area out of the second half of that shear diagram. So that's 1/2 of 936.6 times 15 minus 3.2925. That's going to get me all the way down here to 0 with a 2nd degree constantly decreasing slope curve. My axial force diagram is a constant tension force of 351 pounds. And here it is, the final product of all the shear, moment, and axial diagrams.